Welcome to the second section of Unit 12, where we're going to talk about properties and the mean value theorem of integrals. So let's first revisit the idea of even and odd functions. And so if you recall back to pre-calc of an even function is defined as a function that when you put in negative x, you still get the same output as if you put in positive x. And a way we can see this graphically is that we see it is symmetrical about the y-axis. So for instance, this function right here, which happens to be f of x equal to x to the fourth minus 2x squared, it is symmetrical about the y-axis here, and if we put in a negative 1, we get the same value as if we put in a positive 1. Alright, so it is an even function. Alright, an odd function would be an example of this function over here. We have f of x equals x cubed minus 2x. Okay, and an odd function is symmetrical about the origin. So if you put in a negative x value, you get the negative y value as what you would have putting in the regular x. So if you put in a 1 and get an output value y, when you put in a negative 1, you would expect the opposite of that same y value. So we know with even we have f of negative x gives us f of x, and f of negative x in odd functions gives us a negative f of x. Alright, so we're going to talk about some properties of even and odd functions when it comes to integrals. So first off, let's let a be a positive real number, and f is an integrable function on the interval from negative a to a. So if we have an even function, if f is even, then when we integrate from negative a to a, we can use that symmetry to our benefit. Alright, because just like in the last picture, we saw this even function. So we're going, say this is negative a and we're going over to a here, then since there's symmetry here, we can say that that's the same thing as just integrating from 0 to a and multiplying by 2. Now this works for even functions, only even functions. Now if f is odd, then going from negative a to a, because once again the symmetry is symmetrical about the origin, the areas actually cancel out, and so this integral is just 0. And this is always the case for odd functions. So this is going to help us simplify some integrals a little bit when we have the symmetry in our bounds and we can break it up to even and odd functions. So we notice that we're integrating from negative 2 to 2. If we weren't integrating from negative 2 to 2, then these properties aren't going to apply. But because we're going from negative a to a, we can think, okay, is this function even or odd? And actually the function x to the fourth minus 3x cubed is neither even nor odd, but the function x to the fourth is even, and the function 3x cubed is odd. So we know that some other properties of integrals, the linearity of integrals, we can split this up into two integrals, from negative 2 to 2 of x to the fourth dx, and then subtract the integral from negative 2 to 2 of 3x cubed dx. And so we know that this integral right here is just going to be 2 times the integral from 0 to 2 x to the fourth dx, and we know that this is simply going to be 0. And why is that? Because it's an odd function, so because of the symmetry about the origin, this integral is just going to go to 0. And why do we even want to simplify this even function, you might ask? Well, going from 0 to a number is easier than going from another constant to a constant, because when you evaluate 0, you just get 0 and you don't have to do anything, so we just simply have to evaluate at 2. So we can integrate this and we get x to the fifth over 5, and we want to evaluate that from 0 to 2. Now we could still evaluate this from negative 2 to 2, it just takes a little more computation. Okay, evaluate from 0 to 2, that's just plugging in 2 to the fifth is 32, and then multiply 2 is 64, so we get 64 over 5. So this integral, this entire integral right here, is 64 over 5. Okay, so we're going to use those properties to help us simplify a few things. So now let's talk about the average value of a function. So let's say once again we have a function f that's integrable on the interval a, b, and if we want to find the average value of that function, it's simply 1 over the difference of b and a times the integral from a to b of f of x. And so this basically gives us the sum of all the values in that interval there, and then we're dividing by the interval that we have, and that gives us the average value. Now, what this does is this leads us into the mean value theorem for integrals. And we had a mean value theorem for derivatives, and so it basically said that there has to be a point at which f of c is equal to the average value and all that. Well, this is basically stating the same thing. We're just using integrals to define it instead of derivatives. So let's let f be a continuous function on the interval a to b, and there exists a point c in the open interval a to b such that f of c is equal to the average value. Okay, and so we're going to confirm this with an example here, looking at the function 3x times the quantity 2 minus x. And we want to know, on the interval 0 to 2, at what point does that function equal the average value on 0 to 2? So let's find the average value first. And if you want to look at this graphically, we have the graph right here. This is our f of x graphed. And so it's a parabola, as you would expect. And so we want to find from 0 to 2, and there's no coincidence that those are the zeros of the function, where we're looking at what's the average value in that interval. So let's find the average value. Well, f bar, or average value of f, is going to equal 1 over 2 minus 0 times the integral from 0 to 2 of 3x times the quantity 2 minus x dx. All right, so in order to do this effectively, we do need to distribute and make this 6x minus 3x squared. All right, so when we integrate, we're going to get our average value is equal to, well, 1 over 2. That's just going to give us a 1/2. And then we're going to have, this is a 6x, and when we integrate that, we get a 3x squared minus, and then that's going to be a minus 3x squared. We integrate that. That's going to give us x cubed, and we're going to evaluate that from 0 to 2. Well, when we put in 0, we get 0, and when we put in 2, we get 4 in here, but half of that is going to give us 2. Okay, so this tells us that the average value of our function on the interval from 0 to 2 is 2. Okay, but that's not what our question is asking, or that's not what we're being charged to find here. We're trying to find the points on the interval at which f is equal to 2. All right, so if we look at this graphically, we see that at y equal to 2, we actually have 2 points, one here and one here, and this confirms the mean value theorem. There has to be at least one point if this is a continuous function. We find in our function we actually have 2, and so we want to find what are those points. Well, that is when f of x is equal to 2. And so that means 3x times the quantity 2 minus x is equal to 2. And if we use the quadratic formula, we find that x is equal to 3 plus radical 3 over 3 and 3 minus radical 3 over 3. And that confirms what we find here. This is approximately like 1.577 or so. This is approximately 0.422. And so we look here, yeah, that's a little less than a half, that's a little bigger than 1.5. Those are the points at which we intersect. And so this is using the mean value theorem and using the average value function to find where our function is equal to the average value. And in this function, we see it happens twice. All right, what I want you to do is evaluate this integral that I have right here of cosine theta minus 3 sine cubed theta from negative pi over 2 to pi over 2 using the even and odd properties that we talked about earlier in the video, and then also try these 4 problems out of the book to assist you in practicing the mean value theorem and average value of a function. Thank you.